Good morning. Nice topics that came up. One is networks are the foundation of everything. Yes. With regard to streaming off instruments, we do a lot of that. So I'll talk about that. With regard to MREN, MREN was founded in 1993 as the NSF was getting out of the NSFnet business. A little bit of a deal that I did with Larry Smarr a long time ago. We designed it in 93, implemented in 94, mainly for data-intensive science. So its mission has always been data-intensive science, connecting supercomputers together. But then we got to know Tom DeFonte, who said, let's bring in international. So I'm going to talk a lot about international. We're an international center. MREN is international by default. And when Tom and Larry Smarr were putting together the PRP, we said very early days, we need a GRP, a global research platform also. So the background to this is the NSF and others want these, and we saw this all week, new generation of instrumentation leading to new knowledge discovery, deeper insights into the micro world of molecules, atoms, and the macro world of the universe. We're on the verge of the greatest scientific discovery era in the history of the world, and that's great. And another context is putting this into the National Research Platform, which democratizes that capability, which allows many minds to do new knowledge discovery, to investigate, to understand the tools of science, and that's great. But it needs to be global. We have a rich set of traditions in dealing with the global community in science. Science is global. There's no such thing as borders with regard to advanced science. Open information sharing is a cornerstone of the scientific process, and that's not just the science domain information, but it's also the tools, the capabilities, the architectures, especially with regard to digital capabilities and the cyber infrastructure ecosystems that are being developed. We created the Global Research Platform in large part to share these concepts because they're similar in many cases where you have a large instrument such as the Large Hadron Collider, which we work with closely, generating data but being computed around the world, or a telescope on a mountain in Chile, or radio telescopes in Western Australia. So you can go to this website, see Global Research Platform information. We are supporting the largest science projects in the world. And a thing to note about that is that almost all of them are creating next generation instruments that will generate orders of magnitude more data than the current instrumentation. And this has to flow someplace, and we do the networking that flows it. So there's something called the high luminosity LHC coming. The high luminosity advanced photon source at Argonne National Lab, which is in our neighborhood. Vera Rubin Observatory, much bioinformatics, genomics. People mentioned the inexpensive sequencers coming along, the fusion energy communities, et cetera. So leveraging something called the glyph, we are developing the Global Research Platform to share infrastructure as well as concepts. And we're worldwide, so we have partners everywhere. I'll mention that we also have a workshop once a year. Our last one and last few have been co-located with the IEEE International Conference on E-Science. The last one was in Limosa, Cyprus. The next one, and I'm inviting all of you to join, will be at Osaka University in Osaka, Japan. So just as an example of One of the areas we've become involved in is, for some time, is the Large Hadron Collider Optical Private Network, which takes the data from the Tier 0 at CERN, the Large Hadron Collider, which generates more data than any other science instrument in the world, and distributes it worldwide to do compute. It's on a dedicated private network. But also, there are Tier 2 and Tier 3 centers. These are Tier 1 centers. And that is supported by this infrastructure. It's called the Large Hadron Collider Open Network Environment. This looks very complex, but it's very successful. It's a private overlay network. And the key thing is it works on many, many dozens of different domains, many different organizational structures, many different sites successfully. In fact, it's been so successful that other sciences that are not Large Hadron Collider are using it to do their science, including the Belle 2 experiment, the Pierre Auger Observatory, LIGO, which we heard about yesterday, NOVA, Xeon, DUNE, and others. All of these are particle physics, but they're not Large Hadron Collider, but they're successfully using this. And other scientists, science groups have asked if they could join it. Oceanographers, atmospheric scientists, geophysical scientists. The answer is no, because not everybody can fit in the same boat. So we are conceptualizing something called a multi-one, which maybe can do these, but use the same architecture. And again, sharing and trying to support these folks who a similar architecture. So another example of this is, this kind of model is the square kilometer array, which you see here, which is going to generate even more data than Large Hadron Collider, Western Australia and South Africa, going to compute centers, going to repositories, and being used worldwide. And after 2 years, the people not involved in the funding of the project, such as the US, will be able to have access to the data. So all of those petabytes will flow the other direction after 2 years of the start. Another example is the Belle 2 collaboration, and there are many more. We've had representatives from many of these projects at the workshops, talking about their architecture, talking about their services, talking about their technologies and their futures. Some of the key issues are orchestrating among multiple domains. It's something Google hasn't had to worry about, or Verizon. We do, because any given project can cross at minimal 8 domains. Sometimes it's as many as 24 domains. We also have to deal with high capacity data WAN flows, and that's one of our focuses, is moving toward 400 gig end-to-end, disk-to-disk transfers, 800 gig, 1.2 terabits, and high fidelity data flow monitoring, visualization, and bringing, of course, AI into the equation. And I'll mention some of the work we're doing there. All of this requires international test beds, because you have to test the capabilities before you put them into production. And that's something that we also do with our partners. We have a lot of building blocks to do this with. You heard Tom Lehman, if you were at the international session yesterday, talk about the auto goal. These are the open exchange points that support this type of science worldwide. This is the infrastructure. Another partner is ESNet 6 that you see here. They're very attuned to science, and they created the Science DMZ, of course. Another partner, Internet 2. And here's Jen Leger's quilt map. Something new. Press announcement went out yesterday. This is a 400 gigabit national backbone. And it's going to be a great resource. It's not quite 100% production. It's kind of a quasi prototype, and it's oriented to doing research as well as production, large-scale production science. And of course, there are equivalents around the world. I mentioned a key resource are these open exchange points. We now have at the StarLight facility over 24 400 gig connections and about 110 100 gig connections. And these are the international connections at StarLight. Again, one of the legacies of Tom DeFonte, who started StarTap in 1997. So I mentioned in order to create the future, you need a crucible of creativity for next-gen science and techniques and technologies. We need test beds to do that, and we're currently supporting 28 network test beds to do this. We do the experiments, we do the testing, we put them into prototype if they're successful, and then we integrate them into operations. One nice thing that we're able to do with our partners is have that flow all the way from research test beds to production, because we run production networks and exchanges such as StarLight and MREN, which is a 7-state, should have said this earlier, a 7-state regional network. SciNet is put together every year as part of the supercomputing conference as a test bed in order to do experimentation and demonstrations of emerging technologies. This is Tom Lehman's chart of what it looked like for SE23. We're preparing for SE24. This is what we configured at StarLight in order to support the network research exhibitions for SE. This is what's put together on the show floor for supercomputing. This is another view. This is the Caltech booth and the StarLight booth. And that's a terabit coming from the ceiling into our booth. We were doing terabit flows. These are some of the innovations that we were showcasing and experimenting with. I won't go down all of these. I'm going to talk about some of these individually. One is a project with CERN called NOTED, the network optimized for the transport of experimental data. It's an AI-based model which looks at the flows coming out of the Large Hadron Collider, and based on the historical pattern of those flows, predicts what flows will be where in the future, and then does real-time provisioning. It has about a 95% fidelity in prediction, which is the superpower of AI, which is great. So that was showcased at SE23, and we have another version coming up for SE24. We work with the Naval Research Lab on scaling processes that start very small, but use eventually supercomputers and multi-hundred gigabit flows. We work with the NASA Goddard Space Flight Center. They're into climatology and atmospheric space exploration, of course. They hold the world record for disk to disk across wide area, and they're currently very close to 400 gig disk to disk on the wide area, which is a challenge. Another project, I mentioned NOTED. A related project is something called SciTags, which is identifying individual science flows and provides a capability for steering of those individual flows and doing traffic engineering based on the science group. Another project is interrelating the data transfer nodes among the different science projects and integrating them. Jim Chen, who's here, one of our members, is working on DTN as a service so that multiple sciences can use the same DTN and share the capabilities. We have another AI project, which is called AI DTN, which has an AI model that's doing the analysis of the many parameters that change over time as you use DTNs, especially spread among multiple projects. Another project we're working on with the ESNet testbed is particularly interesting. It's using the smart capabilities that are inside the network so that you can keep your flows inside the network and not put them outside the network to do capabilities. So for example, there's smart NICs, there's very smart processors and switches, there's FPGAs. So I noticed in some of the presentations on AI, they talked about moving to certain processors from the network and then back in. With this capability, you don't have to do it. You can leave everything inside the network. And this is doing gamma ray energy tracking, keeping the flows in the network. Similar related project is this one. This is preparing for the high luminosity advanced photon source. Right now, the pipeline is to collect data out of a pod coming across the synchrotronic sample at the instrument, and then moving it to a repository, and then moving it to a supercomputer and doing the analytics. So now that process takes quite a while. And often the researcher finds the sample should have been moved 3 degrees to the left, and then they have to do it again. So with this process, it's a direct pipeline from the advanced photon source directly to computer memory where it could be steered in real time. We have a couple of P4 test beds that we're doing for a variety of different projects related to manipulating traffic. So it's traffic engineering, it's denial of service defense, and other capabilities. This one is mainly in Asia. This one is in Europe, and it's a project of Géant. We're working on name data networking for science with Northwestern University in Boston. This is the Chameleon test bed, which I'm PI on, so I'm mentioning that, and it's a resource available to all of you, and we need to integrate this with the National Research Platform because it's got great resources, and it is easily configurable and integratable to the National Research Platform. You all know about Fabric. For SE last year, we generated 6 terabits as a showcase. Another test bed is the Supercomputing Asia test bed. It's called the Data Mover Challenge, and this was staged last year, and results were announced in February in Sydney. Another project has been the Data Challenge, which is preparing for the high luminosity LHC. This is some of the data. It successfully met its initial challenges. And this is some of the Asia. Now, next week is the OFC conference, and this is a test bed that was created by the OFC organizers. We'll be doing some demonstrations there in end-to-end 400 gig. This is Tom Lehman's chart, which is a test bed that was created for the NRP and Fabric and OFC. So you see there Fabric, and the purple is NA Rex, and the green boxes are ESNet being configured as one test bed where you can do a variety of things. This is the contribution for StarLight, and Sienna created this traveling Fabric node so that they can send a Fabric node to individual sites such as OFC in San Diego next week. We have been doing 400 gigabit end-to-end for this week, and we'll be showcasing this last week. We're getting close to 400 gig end-to-end across thousands of miles. And then Frank asked a bunch of people to support his project, which is kind of cool. It's a exercise of the CMS software stack, Ruscio as a data manager, FTS as a data mover, and XRD as a data storage device over thousands of miles. So that is being done now. And it's a great example of what you can do when you have these persistent resources and distances. You can have many different paths in many places and exercise the protocols. And that's being done. And then finally, just a couple minutes, looking forward to the future, we have a quantum networking testbed that we're developing to integrate the quantum computers that will show up at Fermilab and Argonne Lab and our university and other universities. Right now, there are no quantum repeaters, so you're limited to 150 kilometers. It's on dedicated fiber. And one of the things that we did last year for OFC was we showed that you can co-propagate classical channels and quantum channels in the same fiber. We were doing 100 gig at OFC and getting, for the long loop, it was about 17 miles, short loop, 2 kilometers. We were getting 95% fidelity on the shorter loop, which is really good for quantum networking, and 91% for the longer loop. That's our setup, including our photon detector, which is using cryogenically cooled wires. Again, we're doing this specifically to connect computers in the same way the internet was created to connect supercomputers. There will be quantum computers in our neighborhood soon. Another project is preparing for the high luminosity LHC, which will require terabit connections end to end. So we're building a prototype end-to-end test bed with 400 gig DTNs on either side to stand up that service. And we're working with Sienna on that, on their Sienna test bed, which is going to provide another 1.2 terabits. And with that, I'll thank everybody and take any questions you may have.
So, Joe?
Yes.
I want to compliment you on all your maps. I've worked with you early on these things. It's a daunting problem. If you want to cause any of the AI, generative AI programs to hallucinate, ask them to describe our networks. You get the weirdest, phenomenally...
I've tried some of that, yes, and I have seen the hallucinations.
Yeah, it's really
they're
funny.
Pretty funny.
Yeah, it's hilarious.
ChatGPT told me that iCare was founded by Argonne National Lab and Fermilab. Yeah.
So, can you go back to the new kid on the block that was just announced and say a little bit more what that is about? The 400 gig, the new 400 gig network.
Yeah, it's a great resource. Okay, so you see the partners on the right and the sites on the chart. This is a 400 gig backbone. It says 100 to 400 because there's a couple segments that won't be there for a while, such as between Chicago and Montreal. But this is a great resource, and it can do end-to-end 400, which most places can't.
And this is, what's the usage business model? Who can use? How can use?
The target usage is research, as in scientific workflow research, networking research, new innovations on the network, plus production for science.
Mm-hmm. And you have Los Angeles a specific wave. Does that mean that if I peer in Los Angeles with specific wave, I can peer into it?
Yes.
Cool.
Yes,
Thank you.
Can. And you're welcome to do so. Yeah, we're preparing some demos. Supercomputing is going to be in Atlanta this year. So.
Hello, thank you very much. A quick question. What is the latency between those nodes?
It varies by site, but it ranges from a few tens to 120.
Thank you very much.
Yeah. Speaking of distances, I should have mentioned on the quantum, I mentioned the limitation of 150 kilometers because there's no quantum repeaters. Not true of line of sight. So you can go to satellites for thousands of miles, and maybe that's how we will connect to the various NRP sites is satellite. That's a potential. Also, our friends in the Quantum Center at the University of Illinois, Urbana-Champaign, are using drones to do line of sight to get from Urbana-Champaign to Chicago. So maybe that's a possibility. Other questions? All right, we are at a break.
Yep, we have a break.
Thank you.